Oh, that's nice, Jared.
I know, it's just.
On. Somehow, some
Okay.
way.
Good afternoon.
No.
Howdy.
Too much work.
Welcome back to, this is almost the last lecture for the semester. We have one more lecture on Monday, and then on Wednesday we have our third partial. So a week from today, we're going to have our third partial exam. Okay, so today we're going to cover the last topic that is going to be included in the exam. What I'm planning for Monday is to have a couple of practice exercises for you to practice this material, and also we're going to go over the review. So you should expect something similar in terms of type of exam, something similar to what we have seen so far. So a first part with multiple choice or true or false questions, and then the second part of the exam will have a problems such as the one we discussed in class and the other one similar to the ones we discussed in the homework, or we covered in the homework. Okay? So the first thing we're going to do today is to collect the homeworks. So if you can pass the homework to this side of to your left. So we're going to have a homework posted tonight, which is going to cover part of the material for today and also the material we cover on Monday. So that should be your last homework. Yeah, it's important as you have seen in class, I never collect the homeworks that are due the day before the exam or the lecture before the exam, because the idea is for you to work on the problem, to discuss them in class, so you can have the homework to study for the exam. So again, I'm not going to lie to you, I'm not going to collect the homework on Monday, so you can work on it. Okay? So we can discuss it on Monday. More homework? So make sure that you write your name. Usually have one or two homework with your own name. So if you haven't turned in your homework, just submit it by the end of the lecture today. I brought the homework number 9. It's graded, so I will pass it around by the end of the lecture, so you can have it by today, so you can study for the exam. Okay? So again, we have our third partial. It's going to be next Wednesday. I believe it's December the 5th. So we're going to be doing the time period of the lecture. And make sure you come. Make sure that you work on your formula sheet. This time we're going to have several formulas, so make sure that you have all those formulas in your paper. And that's it. So today we're going to cover a new topic. And this topic is a very important topic. I'm going to cover only part of it because of time restrictions, but I'm pretty sure that you're going to be seeing more of this test of hypotheses. So before we get to the material, since this is going to be the last topic for the class, I just want to go back and review the objectives for this course. So again, we have 3 main objectives. These are listed in your syllabus. The first one was develop simple graphs and compute summary statistics and interpret their meaning for solving engineering problems. So that was the first thing we did in class. The second objective was to use the probability models to describe uncertainty and make decisions. So we spent, I'll say, 1/3 of the course going through these objectives. And the last objective is the last material we have been covering in class. So we use of sample summary statistics to make inference about underlying means, variance, and proportion to solve engineering problems. So these are the main objectives for this class. And if we go back to our map for the course, these are all the topics we have covered. The last one is the one that we're going to cover today, hypothesis testing. So if we go over the goals, the first one was covered when we covered this material, the measures of location, measures of variability. The second goal was covering this part of the course topics when we cover probability of an event, random variables, probability distributions, and so on, and joint probability distributions. And the third goal of this course is the one that covers the sampling distribution, sample estimation, and hypothesis testing. So these are all the things that you have learned in class and also throughout the semester. So as you can see, the goals of the course are almost completed. So going back to the material we started before the break, we started talking about inferential statistics, and we already covered the estimation portion. So for estimation, basically what we were doing is we were talking about samples, and you were collecting samples from the population. You were computing statistics based on the sample. So for example, you can compute the mean taken from a sample, and then based on that statistic, you were performing some confidence estimation, confidence interval, that will tell you your confidence in terms of the statistics that you compute based on the sample. Okay? So this is the estimation portion of the inferential statistics. Any questions? Okay, so we cover confidence intervals for the mean, we cover confidence intervals for the variance, and for the proportion. So you can make such type of experiments based on the sample, and you can compute confidence intervals for such type of statistics. Now we're going to transition to the second part of the inferential statistics topic, which is hypothesis testing. And in this part, what we are interested in, we are still sampling from the population, but now we are making some statements based on what we want to find out about the sample and about the population. So for example, one statement that we can make is, I believe the population mean age is 50. So when you get the information from the sample, you find out that based on the sample, you find a different number. So the sample mean was 20. So now you will make a decision, or you will make a statement based on the information that you get from the sample, whether you reject or does not reject the hypothesis that you make. Okay? So we are interested in presenting a statement and testing that statement based on a hypothesis test. That's the type of thing that we're going to be doing in this topic. Okay? So, for the agenda for today, we have the general concepts about statistical hypotheses, the role of probability in hypothesis testing, and how to state a null and alternative hypothesis. Also, we're going to talk about testing a statistical hypothesis. We're going to talk about the probability type 1 error and the probability type 2 error, and the role of these errors and the sample size for our hypothesis test. Okay, so here are the objectives in terms of learning, structure, engineering, decision-making problems as hypothesis test. Test the hypothesis of the mean of a normal distribution using either a z-test or a t-test procedure. I don't think we're going to have time to cover this part, but we're going to talk about how to use the z-test to test our hypothesis. And we're going to talk about the p-value and when making decisions. And if we have time, we're going to talk about this the relationship between confidence interval and hypothesis test. Okay, so let's start with the topic. Any questions? So let's try to define what is hypothesis and why hypothesis testing is important. So often the problem is not the estimation of a population parameter, rather the formation of a decision procedure that can produce a conclusion about something. Okay, so right now, we are not interested in estimating a specific parameter. What we're trying to do is to, based on the information of the system, we're going to make a decision, and we're going to test that decision using a hypothesis test. So, for example, a medical researcher may decide on the basis of experimental evidence whether coffee drinking increases the risk of cancer in humans. So, we want to test if coffee is making any impact on this cancer species or the increase of this cancer in humans. So, the researcher is going to postulate conjectures about the system. So we're going to make a hypothesis and we're going to test that hypothesis. In this case, we want to test if coffee is making some impact on cancer. Okay? So another hypothesis is, well, a hypothesis then is a belief about the population parameter. So parameter is, for example, the population mean, the proportion, and the variance. We're going to make an inference about that. And it must be stated before the analysis. So here I have an example, so I believe the mean GPA of this class is 3.8.
Is that your plan for the...
Yeah, that's my plan for the end of the semester. So I'm gonna test this hypothesis. Yes, based on my, I'm gonna take a sample, I'm gonna test my hypothesis, and I'm gonna let you know if that hypothesis is true or not.
Well, I was thinking you would just prove it that.
Not necessarily. So that's why we need to state the hypothesis before the analysis. Okay? So I don't know if that's true or not. That's my hypothesis. Okay? So the conjecture can be put in the form of a statistical hypothesis. So a statistical hypothesis is an assertion or conjecture concerning one or more populations. So the truth or falsity of a statistical hypothesis is never known with absolute certainty. Okay? So again, our analysis is based on a sample. We are not considering the population, unless we examine the complete population, which is not the case. So we take a random sample from the population of interest, and we use the data to provide an evidence that supports the hypothesis. So we make a hypothesis. Let's say my hypothesis is 3.8 for the class. I take a sample. That sample is going to give me some evidence to accept or reject the hypothesis. Okay? So inconsistent evidence from the sample leads to a rejection of the hypothesis. So if I take a sample and the GPA for that sample is 2.5, then I'm going to reject my hypothesis. Okay? So the decision procedure must include an awareness of the probability of a wrong conclusion. So suppose that the hypothesis postulated by the engineer is that the fraction of defectives, P, this is our statistic, in a certain process is 10%. So I'm taking a sample from this process. Let's say I'm manufacturing computer chips. I'm taking a sample of 100, and then I found out that 10 of them are defective. So before I make that experiment, I'm stating that hypothesis. So the experiment is to observe that a random sample of the product in question. So again, suppose that you take a sample from, and then 12 of those items are found to be defective. What we can conclude about this hypothesis. So our hypothesis was that 10% was defective, but we found out that was 12. So does that necessarily make a case for saying that 10% is not the true proportion? No, right? Because it's very close. So it is reasonable to conclude that the evidence does not refute the condition that P equals 10. So it might lead one to not reject the hypothesis. So, however, it is also does not refute that the probability equals 0.12, or perhaps a little bit higher, like the probability, the proportion equals 0.15. Okay? So As a result, the analyst must understand that the rejection of a hypothesis implies that the sample evidence refutes it. Okay, so we're going to have to find out if our sample evidence is strong enough to reject the hypothesis. Okay, so another example for our proportion of defective hypotheses. Let's say that now we find that 20 is the number of defective items. So that could be evidence for rejection. Why? So if indeed 10% is the probability of obtaining 20 or more defective, then if you know this probability and you compute the probability, knowing that this is true, you compute the probability of finding 20 or more, then you will find out that that probability is 0.002. Okay, so you remember the probability given that you know a fact. This is how you compute this probability. With the resulting small rates of a wrong conclusion, it will seem safe to reject the hypothesis that P equals 10%. Okay, so if the probability is really 10% and you take a sample and you find out that 20 are defective, that's telling you that something is wrong with your hypothesis. So the rejection of a hypothesis tends to all but rule out the hypothesis. The acceptance or the failure to reject does not rule out other possibilities. So something that we need to make clear about hypothesis testing is that we never use this term. And I'm using it here just to, as a matter of explanation, but for statisticians, and usually we don't say we accept the hypothesis. What we say is we fail to reject the hypothesis. Okay, because what we are saying is we don't have enough evidence to say that the hypothesis is true. Okay, so we fail to reject it. As a result, the firm conclusion is established by the data analysis when the hypothesis is rejected. So the strong conclusion is made. Okay.
Gas leak.
It's the first time to see. So that's not something that will like, yes, ma'am, okay. Someone here, you never know. Is that close to here? Okay, so we can continue. Okay, so don't be alarmed. Everything is fine. We can continue. Okay. So.
Oh no, we're not the
The worst thing that can happen is that we will leave, and then I'm going to record the lecture, and then you're going to have to take the exam anyways. Okay, so let's complete the lecture. And, okay, so that's not going to happen. So the statement of a hypothesis is influenced by the structure of the probability of a wrong conclusion. Okay, so the statement of a hypothesis is influenced by the structure of the probability of a wrong conclusion. So again, the only strong recommendation that we can make is based on rejecting a hypothesis. So the statement of a hypothesis is very important, because if you want to make a strong conclusion, then you're going to have to reject your hypothesis. So the way you state your hypothesis is going to lead you how on making a final decision with more certainty. So if the scientist is interested in supporting a contention, he hopes to arrive at the contention in the form of rejecting a hypothesis. Okay? So if you reject a hypothesis, then you're sure that you're making the right decision. But if you fail to reject the hypothesis, then you're not sure of your final decision. Because the only thing you're saying is that you didn't find enough evidence to reject the hypothesis. So let's look at these two examples. So if the medical researcher wishes to show a strong evidence in favor of the contention that coffee drinking increases the risk of cancer, the hypothesis tested should be on the form, there is no increase in cancer risk produced by drinking coffee. As a result, the contention is reached via a rejection. Okay, so if we reject that hypothesis, then we are saying that coffee drinking is increasing the number of cancer patients. Okay, is that clear? So the way you state this sentence is helping you to reject the hypothesis and arrive to the conclusion you want to arrive. Okay, so in this case, the researcher is trying to show that the cancer increase is caused by coffee drinking. Okay, so in the second example, to support the claim that one kind of gauge is more accurate than another, the engineer tests the hypothesis that there's no difference in the accuracy of the two kinds. Okay, so again, we state the hypothesis saying that there's no difference, but what we're trying to show is that there's a difference. So if we reject that hypothesis, then we're saying that there's a difference between the two types. Okay, so conclusion. The formal statement of the hypothesis is very important. Okay? So the formal statement of the hypothesis, again, is very important because it's going to lead you to arrive to the conclusions you want to arrive. So the null and alternative hypothesis. So the structure of a hypothesis testing will be formulated with one use of the term null hypothesis. Okay, so now we're going to explain what is a null hypothesis. We're going to have two types of hypotheses, the null hypothesis and the alternative hypothesis. So the null hypothesis refers to any hypothesis we wish to test. And that one is denoted by H0. Okay, so H0 is our null hypothesis. Okay, so the rejection of H0 leads to the acceptance of the alternative hypothesis. And the alternative hypothesis is denoted by H1. So we're going to have two hypotheses, H0, the null hypothesis, H1, the alternative hypothesis. Okay, so the alternative hypothesis, H1, usually represents the question to be answered. So this is the question we want to answer. The null hypothesis basically opposed to H1 and is often the logical complement of H1. Okay, so we formulate our H1 hypothesis and the complement of that hypothesis will be our null hypothesis. And we're going to see this with some examples. So the analysts arrive at one of the two following conclusions. We reject the null hypothesis because of sufficient evidence in the data, or we fail to reject H0 or the null hypothesis because of insufficient evidence in the data. Okay, so we are making these decisions based on the sample we collect from the population. So we take a sample from the population, we analyze that sample, and we verify if we are able to reject or fail to reject the hypothesis, the null hypothesis. Okay, so for example, in our binomial example, the practical issue may be as concerned that the historical defective probability of 10% no longer is true. So the conjecture may be that P exceeds that 10%. So if that's the case, then we want to formulate our hypothesis using the following format. So we know that our null hypothesis is saying that the probability equals 10%. Okay, but the alternative want to test if that probability or proportion is actually higher. So we can state our alternative hypothesis using a greater sign with the proportion being greater than 10%. Okay, so we want to find out if actually that proportion P is greater than 10%. Okay, so this is again the same example. Let's say that 12 defective items out of 100 does not refute the 10%. So the conclusion is fail to reject A0. Okay, so 12 out of 100 is close to 10%. So we fail to reject that hypothesis. And I'm going to show you how to make that decision based on a probability statement. But for now, I just want to understand how these decisions are made. So if we find out that 12 is not sufficient evidence, then we fail to reject A0. On the other hand, if the data produce 20 out of 100 defective items, then the conclusion is reject H0 in favor of H1, saying that the probability is greater than 10%. Okay, so here is how I want you to make the decision, or your conclusions has to be stated in one of these two ways. Fail to reject H0, fail to reject the null hypothesis, or reject the null hypothesis. Okay, any questions? Say that again?
How do you want us to state that?
So I'm going to show you how to make the actual test based on the probabilities. So for now, I'm just saying if this is the case, this is the conclusion. But after you make the actual test, then you're going to have to state your conclusion. And the conclusion has to be in one of these two ways. So if you're going to fail to reject H0, or the conclusion is going to be reject H0, or your null hypothesis. Any other questions? No? Okay. So, another example, I think this is the best example for you to understand how these hypothesis tests work. So, here we're looking at the predicament encounter in the jury trial. So, we have the null and the alternative hypothesis stated on these two ways. So, we have a person, we are going to take this person to trial, and we have these two hypotheses. The defendant is innocent, or the defendant is guilty. Okay, those are the two questions, the two options that you have. Okay, so the indictment comes because of the suspicion of guilt for this person. So the null hypothesis stands in opposition to the alternative hypothesis and is maintained, unless the alternative hypothesis is supported by evidence beyond a reasonable doubt. Okay, so failure to reject the null hypothesis in this case does not imply innocence. Okay, that doesn't mean that the person is innocent, but that the evidence was not sufficient to convict, and that the jury does not necessarily accept H0 but fail to reject the null hypothesis. So if you don't show enough evidence to find this person guilty, then you're going to have to reject the null hypothesis. Or do not reject the null hypothesis. Okay? Okay, so now that we know how to state this hypothesis, again, we have two types of hypotheses. We have the null hypothesis and the alternative hypothesis. One is the complement of the other, and we are trying to make a decision based on the information we have from the sample. So the type of decision we can make is reject the null hypothesis or fail to reject the null hypothesis. Okay, so those are the important concepts from that part that we just discussed. Now we're going to test our statistical hypothesis. So let's think about these examples. So a certain type of cold vaccine is known to be 25% effective after a period of 2 years. So you're giving this vaccine to the people, and after 2 years you find out that this vaccine is only effective to 25% of the people. Okay? So to determine if a new vaccine is superior, providing protection for a long time, 20 people are chosen at random and inoculate, and we are testing a new vaccine with these people. Okay? If more than 8 of these receiving the new vaccine surpass the 2-year period without contracting the virus, then the new vaccine is considered better than the previous one. Okay? So this is the problem. We have a new vaccine, we want to test that vaccine, and we want to find out if it is more effective after 2 years. Okay, and we're going to take a group of people, we're going to show that this vaccine is more effective or not. Okay, so the alternative hypothesis is that the new vaccine is superior. Okay, so the new vaccine is superior is our alternative hypothesis. So this is equivalent to testing the hypothesis that the probability of success on a given trial, that's P equals 1/4, against the alternative that P is greater than 1/4. And why is that? Because the probability of success is 0.25, so that's equal to 1/4. And that's the success rate that we have from the original vaccine. We want to test the new one, and we want to find out if it is more effective, so that means that that probability has to be greater than 1/4. Okay, so this is usually written as follows. Our null hypothesis equals 0.25, and our alternative hypothesis equals is greater than 0.25. Okay, does that make sense? So we have a new vaccine. We know that the original vaccine is effective only 25%, so that's our null hypothesis. Our alternative hypothesis, we are trying to prove that the new vaccine is better. So we want to test if the probability after 2 years for the people taking the new vaccine is greater, so we can have more than 25% of the patients having a good effect of using the vaccine. Okay, so the test statistic on which we base our decision is X, is the number of patients that are basically responding to this treatment. So the number of individuals in our test group who received the new vaccine. The possible values of X are divided into 2 groups, the numbers that are less or equal to 8, and the numbers that are greater than 8. Okay, so why are we doing that? We established our probability already, 0.25, but we also have this requirement, and we know that 8 of the patients that took the original vaccine were responding to the treatment. Okay, so we want to find out if we can find a number greater than 8, so we can establish that our new vaccine is better. Okay, so all possible scores greater than 8 constitute the critical region. So the last number observed when passing into the critical region is called the critical value. So in our case, again, we have our hypothesis, 0.25 and greater than 0.25. We're going to establish our rejection region for the null hypothesis. The null hypothesis is saying that the probability is 0.25. So the rejection region is if that probability is greater than 0.25. And also, we have a critical value, which is 8, which is the number of patients that actually passed the test for the first, for the original vaccine. So that 8 is going to define our rejection region. So if we find more than 9 or more patients responding to the treatment with the new vaccine, then we're going to reject our hypothesis, null hypothesis. Okay, so that means that we have enough evidence to say that our hypothesis is rejected. Okay, so again, the critical region based on the number of patients, the probability is based on the hypothesis is 0.25. Okay, so if X is greater than 8, we reject H0 in favor of the alternative hypothesis. If X is less than or equal to 8, we fail to reject our null hypothesis. So the decision procedure is just described to lead to either 2 wrong conclusions. Okay, so we have to deal with something else before going to the test of our hypothesis. We are making these decisions based on our samples. So we can make two possible wrong conclusions. For instance, the new vaccine may be no better than the one in use, and yet in the sample we find that more than 8 surpass the 2-year period. You were lucky enough to find out a sample that has more than 8, so we can make a conclusion based on that sample. So that conclusion is going to be wrong. So that's one possible error. Rejecting H0 in favor of H1, when in fact H0 is true, is called type 1 error. Okay, so that's the first error that we're going to discuss. So the rejection of the null hypothesis when it is true is called the type 1 error. So if you have your null hypothesis, and based on the population, that hypothesis is true, but you take a sample, you make a conclusion based on that sample, and you reject that hypothesis, you are making this error. Okay, so we want to minimize the probability of doing this error.
It's probably straightforward, but what is the significance of the value between 8 and 9 to reject and not reject?
So based on this problem, we know that for the original vaccine, 8 of the people passed the test of 2 years. So that's why this number is important. Because if we want to show that our new vaccine is better, we have to find more than 8 people passing the 2-year period. Okay? Any other questions?
Oh, so that's just the example.
Yes, it's an example. Yes, it's based on the example.
Yeah.
Okay? So, a second type of error is committed if we fail to reject H0 when in fact H0 is false. So this is called type 2 error. Okay? So we know that it's true and we reject the hypothesis, type 1 error. If we fail to reject when in fact it's false, type 2 error. Okay? So in testing a statistical hypothesis, there are 4 possible situations that determine whether the decision is correct or not. And this table basically shows you those errors. So again, you have 2 possibilities. The null hypothesis is true or the null hypothesis is false. If you do not reject H0 when it's true, then you're making the right decision. But if you do not reject H0 when it's false, then you're committing type 2 error. If you reject H0 when H0 is true, then you're committing type 1 error. But if you reject H0 when it's false, then you're making the right decision. Okay, so again, what we're trying to do is based on the sample, make a conclusion, but making that conclusion based on the sample can lead you to 2 different errors, which are listed here, type 1 and type 2. And again, if you have the complete information of the population, you will not have to deal with this because you're going to make the right decision. But again, we are dealing only with a sample of the population. So we are trying to make a conclusion only based on some units from the total population. So that can lead to 2 different errors, the type 1 and type 2. Okay, and we want to minimize the probability of making these errors. Okay, so 2 types of errors, type 1 and type 2. Okay, so the probability of committing a type 1 error is also called the level of significance, and is denoted by alpha. So in our example, a type 1 error will occur if more than 8 individuals pass the 2-year period without the virus, and researchers conclude that the new vaccine is better when it is equivalent to the one in use. Okay, so that would be type 1 error. If X is the number of individuals who remain free of the virus for at least 2 years, then we can find that level of significance or the probability of type 1 error by computing this probability. So again, this is a binomial experiment. It's whether pass or not pass. it is defective or not defective. So for those type of experiment, we use a binomial distribution because we have a Bernoulli random variable. So when we have that type of experiment, we can compute this probability, the probability of x being greater than 8, when we know that the probability is 0.25. So we use a binomial distribution. How do you find this probability? Using the binomial, you have to add from x equals 9 to x equals 20, because 20 is the sample. So that probability is the one that is stated here, the summation from 9 to 20. The n is 20, the probability is 1/4. And the easiest way to find this probability is by looking at the complement, right? So 1 minus the summation from 0 to 8 of the same probability. So you find out that the level of significance is 0.04. Okay, so that's a very low probability. Okay, so the null hypothesis, the P is equal to 1/4, is being tested at a level of significance, or the probability 1 of type 1 error of 0.04. So the critical value is very small, and it is unlikely that a type error 1 will be committed. Okay, so you computed this probability of type 1 error, and you find out that the probability is 5%. That's a very small probability. So that's telling you that you're making by accepting or by not rejecting the null hypothesis, you are making the right decision with this level of confidence. Okay, so it will be unusual for more than 8 individuals to remain immune to a virus for 2 years. So the new vaccine is essentially equivalent to the one now on the market. Okay, so you fail to reject the null hypothesis, you know. What was that? Okay. Okay, that's fine. That's fine. Okay, so going back to the example. So the critical value is very small, so you can make that conclusion. And the probability of committing this type 1 error is very small, so you have good confidence that your decision is correct. Any questions? Okay, so the probability of type 2 error, this one is impossible to compute if no exact alternative hypothesis is stated. And when I say exact, is that you have a probability equal to. Okay, so if you're using a value larger than or less than, you will not be able to compute the probability to error, type error. Okay, so if we test the null hypothesis that the probability is equal to 1/4 against the hypothesis that the probability is equal to 50%, then we are able to compute the probability of not rejecting H0 when it is false. So that probability, to compute that, of obtaining 8 or fewer in the group that subscribes a 2-year period with this probability, again, you are computing the complement of the hypothesis type 1. So now you're looking at the probability of x being less than or equal to 8. But in this case, for the alternative hypothesis, we have the probability equals to 1/2. So if you find that probability, you'll find that that probability is 0.25%. 25% is kind of big value. So there's a high probability. It is likely that we shall reject the new vaccine when it is superior to the one it is used. Okay, so you're computing this type 2 error, and you find that that probability is 25%. That is telling you that it's a 25% that you can commit this type 2 error, and that's a large value. Okay, so the final conclusion that you will make is probably wrong. So it is always possible to reduce this type 2 error by increasing the size of the critical region. Okay? So initially we considered the critical region with 8 greater than 8. Now consider what happens if we change the critical region to 7. So in testing the probability equals to 1/4 against the alternative hypothesis that equals 1/2, we find out that the probability of having a type 1 error is 0.10. Again, we are changing our critical value to 7. So now the probability goes from x equals 0 to 20 instead of going from 9 to 20. So we are adding an additional unit, and we find this probability is equal to 10%. So you see that there's an increment in that probability. Originally it was 0.04 or 4%. Now it's 10% just by changing the critical region by 1 unit. And if you look at the probability of type 2 error, now you see that there's a reduction of that probability as well. Now it's 13%. So you can reduce the size of this probability to type 2 error by changing the critical region. Okay, so we change the critical region, we reduce the probability of type 2, but we also increase the probability of type 1 error, which leads to another conclusion. So you can't reduce both errors simultaneously. So if you decrease one, the other one will increase. Okay? So for the fixed sample, a decrease in the probability of one error results in an increase in the probability of the other error. Okay, so the probability of committing both types of errors can be reduced by increasing the sample size. So this is kind of related to what we saw in confidence interval. So if you increase the size of your confidence of your sample, you will reduce the size of your confidence interval. Same thing applies to this. This is the second announcement of the emergency end. Okay, that's good news. Okay, so shouldn't worry about anything now. So the concepts discussed for the discrete population can also be applied to a continuous random variable. So instead of looking at the previous example in which we're looking at the vaccine hypothesis, now let's look at this different example which involves continuous random variable. So consider the null hypothesis that the average weight of male students in a certain college is 68 kilograms against the alternative hypothesis of unequal to 68. So we can state those hypotheses in this way. So right now, we are looking at two-sided alternative hypothesis. In the previous example, we are looking at greater than, so we are looking only at one side of the event. So the alternative hypothesis allows for the possibility of having mu less than 68 or mu greater than 68. So a sample mean that is close to the hypothesized value of 68 will be considered evidence in favor of the null hypothesis. Considerably less than or more than 68 will be evidence for favoring the alternative hypothesis. Okay, so the sample mean is the test statistic in this case. In the critical region for the test statistic is, let's say we arbitrarily chose this critical region to be the intervals where x bar is less than 67 and x bar is greater than 69. So we can determine this critical region, and then in this figure you can see that you will not reject H0 if it is 68, but you will reject it if it is less than 68 or greater than 68. So again, we assume that the standard deviation of the population of the weight to be this much, 3.6. So our decision statistic based on the random sample of size 36 will be the sample mean. So from the central limit theorem that we studied, the sampling distribution of x bar is approximately normal, 0, 1, or the standard normal. And we know how to compute that standard deviation for such distribution, which is sigma over the square root of n. So we find out that the standard deviation for this x bar distribution is 0.6. Okay, so what is the probability of committing a type 1 error based on this example? So the probability of committing a type 1 error is equal to the sum of the shaded areas, which are these two. So again, our critical region is less than 68, so I start with 67, and greater than 69, so this area. So that's our critical region. So the C values corresponding to x bar 1 equals to 67 and x bar 2 equals to 69, when H0 is true, are, therefore, we can find that alpha, do you remember what alpha means for hypothesis testing? I just mentioned it, but again, it's the level of significance. So alpha is the level of significance. So you can put that probability of type 1 error. That's your level of significance. So in this case, it's 0.09, which is almost 10%. So 9.5 of all samples of this size would be thought to reject mu equals 0 kilograms. In fact, if it is true. Okay? So, to reduce the size of this type 1 error, we have a choice of increasing the sample size or widening the fail to reject region. So we saw that with the previous example. Those are your two options. Suppose that we increase the sample size to 64, then we're going to have this standard deviation, and we can compute the critical region again, and you will find that the probability of type 1 error is now less than the previous one. Now, it went from 9%, 9.5% to 2.64%, just by increasing the size of the sample. Okay? So the reduction in alpha is not sufficient by itself to guarantee a good testing procedure. We must also evaluate the type 2 error for various alternatives of hypotheses. So we were able to reduce the size of our probability type 1. Now we want to find out what will happen with the probability type 2 error. Okay? So if it is important to reject A0 when the true mean is some value greater than 70 or less than or equal to 66, then the probability of committing a type 2 error should be computed for the alternative mu equals 66 and mu equals 7. Because of symmetry, you'll see that for 66 and 70 is the same probability. So it is only necessarily to consider the probability of not rejecting the null hypothesis that mu equals 68, when the alternative is mu equals 7. Because both of them are in the same, they are separated by the same length. So if you go from 68 to 66, you have 2 units. If you go from 68 to 70, it's just a unit. So because of symmetry, you can make your conclusion based on one of the sides. Okay? So a type 2 error will result when the sample mean x bar falls between 67 and 69 when H1 is true. Therefore, we find that the probability type 2 error is the probability of finding x bar within this region when mu equals 7. Okay, so from there we can compute these probabilities. Again, the C values corresponding to these numbers are here, negative 6.67 and negative 2.22. Therefore, the probability type 2 error will be equal to 0.01, which is 1%. So if the true value of mu is the alternative, mu 66, then the value of beta will be again the same number, because of symmetry. Okay? So for all possible values of mu less than 66 and mu greater than 70, the value of the type 2 error will be even smaller when n equals 64. Because when we increase the size of the sample, you know that the error or the probability of committing that error will decrease. Consequently, there will be a little chance of not rejecting H0 when it is false. Okay, because this probability is very small. Okay, so now we're testing the same problem, but instead of using mu equals 68, we're using mu equals 68.5. So we compute the same numbers, and as you can see, that probability is now very high. And the reason for that, now it's almost 90%, just by changing that number. And the reason for that is when you get closer to the actual true value, which is 68, you'll see that that probability of committing type 2 error will increase. Okay? Even though you are more close to the true value, that probability when you get closer to the true value is going to be very high. Okay? So that's just for showing that point. So this, in summary, you can read these 4 points. This basically summarizes what we did in this section. So we know that both type of errors are related. So a decrease of one generally results in the increase of the other. The size of the critical region and the probability of committing a type 1 error can always be reduced by adjusting the critical value. So you saw that. An increase of the sample size n will reduce alpha and beta simultaneously. And the null hypothesis is false. It's a maximum when the true value of the parameter approaches the hypothesized value, which is what you saw on the last part. Okay? So these summarize the important points for type 1 error and type 2 error. Okay, so one very important concept that relates to error probability is the notion of a power of a test. And the power of a test is very simple to compute. The power of a test is the probability of rejecting H0 given that a specified alternative value or hypothesis is true. So the power of the test is just 1 minus the probability type 2 error. So if you compute the probability type 2 error, you can find that power by subtracting 1 from that. So often different types of tests are compared by constructing the power properties. So in the previous example, the power will be 13%. In this case, if mu is truly 68.5, the test as described will properly reject H0 only 13% of the time. Okay, so that's what the power is telling you. So it's 43. Okay, so now we can differentiate between, after discussing these examples, between the two types of hypothesis tests that you can perform. So if you have a test of any statistical hypothesis where the alternative is one-sided, such as this, or this is called a one-tail test. So you're looking at H0 equal to a statistic, and H1 looking at greater than or less than. That's called a one-tail test. But generally, the critical region for these alternative hypotheses are the following: alpha, well, theta equals or greater than theta 0 lies in the right side of the distribution, and the less than of the theta 0 lies to the left of the tail. Okay, so it will correspond to the side of the test. So a test of any statistical hypothesis where the alternative is two-sided, such as this one is called a two-tailed test. And in this case, you're going to have the alternative hypothesis with a non-equal sign, and that states that either the left region or the right region will be considered for your rejection area. Okay, so two types of tests. one-tail, two-tail test. And it will depend on how you state your hypothesis. Okay, so the null hypothesis will often be stated using the equal sign, as you saw. The location of the critical region can be determined after H1 has been stated. So your alternative hypothesis will state will determine the critical region. So in the example, if testing a new drug, one set up the hypothesis testing that is no better than a similar drug now on the market, and test his against the alternative hypothesis that the new drug is superior. So this is kind of similar to the vaccine example. Such an alternative hypothesis will result on a one-tail test with the critical region in the right tail, because you want to test if it is better, so it should surpass the previous test. Okay, so you want to test that is better. You want to find out if you can surpass that region. Okay, so now I wanted to get to this example because here you're going to help me state the hypothesis. So let's look at this problem. So here we have a manufacturer of a certain brand of rice cereal claims that the average saturated fat content does not exceed 1.5 grams per serving. So I want you to state the null and the alternative hypothesis to be used in testing this claim and determine where the critical region is located. Okay, so you have this statement. What type of null hypothesis would you use? I'm going to make it easier. When you state the null hypothesis, it's always equal to. So it will be equal to 1.5, correct? So let's see, the manufacturer claim should be rejected only if, so we have our H0, mu equals 1.5. So this will be rejected if mu is blank, then 1.5 milligrams. So our alternate hypothesis will be equal, not equal, greater, correct. So I have to be greater than 1.5, greater than 1.5 milligrams. Okay? So the problem is saying does not exceed. So you want to test the case in which it is greater than that value. Okay, so we have another example. Can I move to the next one? Yeah. Here we have a real estate agent claims that 60% of all private residences being built today are 3-bedroom homes. To test this claim, a large sample of new residents is expected. The proportion of these homes with 3 bedrooms is recorded and used to test the statistic. So you should state the null hypothesis and the alternative hypothesis to be used in this test. So again, the null hypothesis is A0. So we want to test if that is equal to 0.6 for H1. What will be the alternate hypothesis? Not equal, correct. Because you're not specifying if you want to find greater than or less than. So for those cases, you're looking at both cases, so it's not equal to 0.6. Okay, so the last part of the lecture is actually on the slides that I sent you yesterday. So if you have those, please use those now. And this is very simple. Now we're going to perform a test using the hypothesis. So for the purpose of the class, we're going to focus on the test concerning the single mean. So we're going to focus on the mean of a sample for a single sample. So test on the single mean, when you know the variance, you consider the hypothesis in this way. You have the null hypothesis equal to mu0, or the alternative, which is not equal. And the appropriate test statistic should be based on the random variable x bar. Because again, we are looking at the population mean. And we want to find out if that population mean equals the specified value. So we can determine the critical region based on the computed sample average. Okay, so for this test, we have to compute the z values using this formula. So again, we are basing this on our central limit theorem. So we're going to compute the z values, and when it's greater than z equals z of alpha half, or the z values when it's less than the negative of alpha half. And again, this is looking at the two-sided test. So if we find that z is within this bound, do not reject the null hypothesis. But if it is outside those bounds, then rejection of A0 will occur. With this definition of the critical region, it should be clear that we will probably will be probability of alpha of rejecting A0, when indeed mu equals mu0. So this is how you perform the test for a single sample when you know the variance and it's based on the sample mean. So now the case in which you have a one-sided hypothesis, again, you still know the variance, and this is just one mean. So when you have this hypothesis, now you have a one-sided test. The rejection of A0 results when the computed value is greater than Z alpha. So now you don't have to divide alpha by 2 because this is a one-sided test. When you divide by 2 is when you have the Q side. Okay, is that clear? It's the same case as the confidence intervals.
So on that point,
Yes.
does it say that it's two-sided case? You're saying one-sided case?
This is test of one-sided
On the second
hypothesis.
one,
Yes.
described as a two-sided case.
What is it? Test of one-sided hypothesis on the mean involve the same statistic described in the two-sided test. So you're using the same statistic. The statistic that you're using is the sample mean. That's our statistic. You're estimating the population mean using the sample mean. So we are using the same statistic, but the rejection region is based on one side only. So the rejection region is based on Z alpha. You don't have to divide by 2. Okay? Okay, so let's look at this example. So I'm going to show you step by step how to perform these steps for the problems. And I want you to see this. If I ask you something similar in the exam, I will expect you to step by step describe the procedure. Okay? So if you want to get the full credit for the problem, I want to see the statement of the hypothesis and the step you follow to complete the test. Okay? So first thing you do is to state the hypothesis. So for this problem, you have a random sample of 100 recorded deaths in the United States during the past year, and that showed that an average lifespan is almost 72 years for the people that were collected. Assuming that the population standard deviation is 8.9 years, So again, the problem is telling you that you know the population mean. Okay, so remember, this test will apply when you know the population mean. So does this seem to indicate that the mean lifespan today is greater than 70 years? And I want you to use a level of significance of 0.05. So first thing you do is to state your null hypothesis. So your null hypothesis H0, you say that average is 70 years. And you want to test if it is actually greater than that. So your alternative hypothesis, H1, is mu greater than 70. The level of significance is 0.05. So your alpha is 0.05. And then you have to specify your critical region. So this critical region is going to be used to decide whether you reject or fail to reject your hypothesis. So in this case, Z is found using this value on the standard normal table. So you're going to use the standard normal distribution table with alpha equals 0.05, and that Z value of 0.05 equals 1.645. Okay? So your value, the value that you're going to compute for you to reject the hypothesis, has to be greater than 1.645. Okay, so this is what you're going to use to reject or to fail to reject the hypothesis. Okay? So, step number 5, you're going to compute your C value. And you know that based on the central limit theorem, you find Z equals x bar minus mu 0 divided by sigma square root of n. So you find that value, x bar is 71.8, mu 0 is 70, divided by sigma, we know that number, 8.9, divided by the square root of 800. So that number equals 2.02. So in our case, what would be the decision? So this determines the rejection region. So if Z is greater than this value, we reject our null hypothesis. So our Z value is 2.02. That means that it's greater than this value. So the decision is reject H0 and conclude that the mean lifespan is greater than 70 years. Okay, so important, state your hypothesis, find the critical region, compute your C values, and you can state this step in your formula sheet. That's okay. You can state the hypothesis, find the critical region, compute the C value, and you can write this formula, and then make a decision. That's something that you can add to your formula. Okay? So these are the steps. Now we're going to look at the case in which we have, forgot to pass this. So please don't leave without signing the attendance sheet. And now we have another case, and this is the last problem. So a manufacturer of sport equipment has developed a new synthetic fishing line that the company claims that has a mean breaking strength of 8 kilograms with a standard deviation of 0.5. Test the hypothesis that mu equals 8 kilograms against the alternative that mu is not equal to 8. If a random sample of 50 lines is tested and found that the mean breaking strength is 7.8 kilograms, and use a 0.01 level of significance. So in this case, it's very easy to state the hypothesis because it's given. So mu equals 8 kilograms, and H1, the alternative, equals or not equal to 8 kilograms. So what type of test is this one? This is a one-sided or two-sided? Two-sided, correct? So now we have two critical regions, the one that is greater than and the one that is less than. Okay, so the level of significance equals 0.01, and our critical region is Z less than 2.575, and again this is using alpha hat, so that means that this is 0.005, and Z greater than 2.575. So the next step is to compute your Z. So Z equals 7.8 minus 8 divided by 0.5. The square root of the number we have is 50. So this is minus 2.83. So what will be your decision? So you have this. You have Z equals minus 2.575 and 2.575. So your rejection regions are these two areas. Correct. You reject, you find your critical region. These are your critical regions. You compute 2.83. So that falls in this area, which is the rejection region. So your decision is reject H0 and conclude that the average breaking strength is not equal to 8 kilograms. This is not equal sign. Okay? So that concludes the topic and the material for the exam on Wednesday. On Monday, we're going to discuss some extra problems based on this topic. We're going to go over the review, and we're going to have a time for questions for the exam. Okay, so I have the homework. So if you want to pick your homework, the graded homework is here. And please sign the attendance sheet before leaving. Thank you. Yes. Where's the attendance sheet?
Yeah. Go through all of them.
Yes.
I didn't really get it, or I didn't get my exam from last time.
Yes. If you want to stop by now,
Okay.
I'll be there
Yeah.
in a few minutes. Thank you.
I can't wait that.
Yeah.